Hello everybody, my name is Nguyen-Tu, and this is Lab 2 of Physics 2212. The purpose of this lab is to compare the experiment collected distance dependence of a small bar magnet's magnetic field to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. In this lab, I will be using the Biot-Savart law, which gives us an equation that calculates the magnetic field produced by a moving point charge. Also in this lab, I'll be using the distance dependence equation for the magnitude of a bar magnet's magnetic field given in the lab instructions, and the equation for the magnitude of a dipole's magnetic field when the observation location is on axis with the dipole. For the model calculations, I will also be using a general formula for the magnetic field of a dipole given in the lab instructions. To complete this lab, I'll be following 5 steps. First, with the physics toolbox magnetometer, I will align the phone such that the magnitude of Bx is approximately 0 to compensate for the Earth's magnetic field. Second, I'll measure and record the perpendicular distance from the bar magnet to the phone sensor that causes the magnitude of Bx to equal approximately 20, 70, 120, 170, and 220 microtesla 3 times each. Third, I'll plot the logarithm distances observed against the logarithm x-component magnitude it is associated with to find the value of n. Fourth, I'll measure and record the magnitude of the bar magnet at a location 45 degrees from the bar magnet. Fifth, I'll compare the observed 45 degrees magnetic field to a bar magnet's magnetic field modeled through GlowScript. The main result of my lab is that the observed 45 degree magnetic field magnitude was approximately 130% that of the model calculation. Similarly, the model calculation was approximately 77% that of the observation. In addition, n was found to be negative 2.82 and k to be approximately 6.16 times 10 to the negative 7. Overall, this likely means that there was error when measuring the magnetic field of the bar magnet for this experiment. Shown here is the details behind the bar magnet used in this experiment. The first part of the experiment had the goal of finding n. Shown on the left is how the bar magnet was positioned relative to the phone sensor along with an example image of the physics toolbox magnetometer readings. On the right is the data collected from the app for step 2 of the procedure. Displayed here is the plot for the logarithm distances to the logarithm x-component magnitude it is associated with for step 3 of the procedure. From this graph, I found that n is equal to negative 2.82 and ln k is equal to negative 14.3. The second part of the experiment was to measure the magnitude of the bar magnet's magnetic field at a 45-degree angle from the bar magnet. Shown on the right is how the phone and magnet was positioned with the observed data on the bottom. Of note, the perp is the distance for which the on-axis net magnetic field detected had a magnitude of 100 microtesla. To model the bar magnet for the coding part of this lab, the system is the bar magnet while the surroundings is the Earth. The assumptions made are 1. The magnetometer is only affected by the magnetic fields of the bar magnet and the Earth. 2. The Earth's magnetic field is correctly accounted for such that it has no effect on the bar magnet's detected magnetic field. 3. The magnetometer gives accurate measures of the magnetic fields it experiences. And 4. The location of the iPhone X's magnetometer sensor was correctly located to be on the bottom left-hand side. Displayed here is the first part of the code behind the model. On the left is the physical constant mu0 over 4 pi at the top, the code behind the magnet below that, and the functions for calculating the magnetic field and model key at the bottom. And steps on the right is how mu, the magnet's magnetic dipole moment, was calculated. Shown here is the remainder of the code for the model with the code that creates the on-axis and perpendicular to axis arrows on the left and the code that creates the 45-degree arrow, model key, and camera rotation on the right. In this lab, there are 3 main possible sources of error. First, a single drafting ruler was used instead of 2-meter sticks or measuring tapes, which could cause the distances observed to be less accurate due to conversion. Second, the wooden table the experiment was conducted on had metal screws at the legs. These could affect the magnetic fields detected by the magnetometer. Third, the location of the iPhone X's magnetometer sensor may not be exactly at the location determined for the experiment. This could affect the distances observed in the experiment and thus the distance-dependent calculations like k and n. Now to answer some lab questions. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction because it was oriented that way to compensate for the Earth's magnetic field. As the magnetometer moved closer to the magnet, the measured x component of the magnetic field increased in the positive direction. Therefore, the position of the magnetometer had an effect on the measured x component of the magnetic field because, for example, mispositioning it would cause Earth's magnetic field to be mixed with that of the bar magnet. If my setup was not oriented to compensate for the magnetic north, but at some intermediate angle with respect to Earth's magnetic field, the Earth's magnetic field would be included with that of the bar magnet in the readings for the physics toolbox magnetometer. Therefore, my readings for the bar magnet's magnetic field would be inaccurate if I did not find another means of compensating for Earth's magnetic field, like measuring the magnetic field without the bar magnet in the vicinity and then subtracting its component values from the values found when the measurements of the bar magnet are made. If my experiment were to use 2 identical magnets stuck together end to end instead of 1, I would expect the measurements to approximately double since the Biot-Savart equation has charge in the numerator and we would be doubling the amount of charge. In addition, I would expect the direction to be the same as long as the relative position direction is maintained.